Hi guys, my name is Banu Prakash. This is my first video. I am dealing with the subject strength of materials. In this video, I am going to discuss about the unsymmetrical bending. Before going into the topic unsymmetrical bending, now let us discuss about difference between the symmetrical bending and unsymmetrical bending. As shown in the figure, this is a structure on which the load is applied. This is the cross section. Here the load is applied perpendicular to the plane. Due to the load, the bending is taking place in this plane in only XY plane. Bending is taking place only in the single plane. Whereas if we take as a unsymmetrical bending, this is a beam and these are the axes XY, Z, and the uniform load is acting. When the load is acting, the bending of the beam takes place in two planes, that is in XY plane and XZ plane. Both planes the bending of the beam will be take place. When the load is applied, if the bending takes place only in the single plane, then it is called symmetrical bending. If it is bending in the two planes, then it is called unsymmetrical bending. Okay, now we are going into the topic unsymmetrical bending. In this video, we are going to discuss about stress in the beam due to unsymmetrical bending and the maximum stress obtained in the beam due to the load, and also finding the neutral axis at which the stress applied will be equal to 0 due to the moments in the unsymmetrical bending. Okay, now let us take we know that flexural equation that is the relation m by I equal to sigma by y is equal to E by R. Okay, by using this relation is helpful in this process to calculate the stress values. Okay, now let me take as shown in the figure, this is the beam. Let me take a small cross section of the beam so that we can analyze the complete beam by taking the small section. This is the small cross section of the beam. Okay, these are the axes. These are the axes. Let me take the load and the moment created. This is the load and this is the moment direction. Let me take the points A, B, C, D. This is y axis, this is z axis. Okay, and the moment is m. The load at which acting is inclined at an angle theta. Okay, this is the cross section area we are going to solve. Since it is an incline, it is impossible to solve, so that we are going to split this moment into two axes, that is in this direction and in this direction. Okay, this is adjacent, we get m cos theta, and this is m sin theta. This is the moment created due to the axis MYY. Let me take m cos theta is equal to my and m sin theta is equal to mz. If the axis is fixed, the moment created with the axis is my, m cos theta, and this axis is mz. Okay, now the moment of inertia due to Iyy is equal to moment of inertia due to y axis, and Izz moment of inertia due to z axis. Okay, now by using the above equation, we will take m by I equal to sigma by y, that is the relation. We have to find the stress value, that is sigma is equal to my by I. Okay, here the moment is split into two axes, so the stress is produced from both the moments, that is along y axis and that is along z axis. For both moments there will be stresses, so the total stress obtained will be equal to, stress is equal to my into z by Iyy plus mz into y by Izz. That will be the total stress produced at any point. Okay, now we are going to find the stress values at point A comma B comma C and D. Okay, before we are going to the stress values, as I said, my and mz are moments created. These moments are represented, these moments changes their sign according to their the moment created. Okay, let me show with an example. Consider as this is the plane we are taken, and this is the point A, B, C and D. Okay, these are the moments. This is my and this is mz. Okay, for point A, point B, point C and point D, this is the plane we are considered. As I said before, we have to we have get two moments. Due to the two moments we get two stress values. The summation will get the total stress value. When we are calculating for point A, we will take the moments into the consideration to take the sign values. Okay, due to the moment y, this is acting in this direction, so that the top layer will be compressive in this direction. Okay, so that due to the moment my, there will be compressive moment. Due to mz, this AC layer will be tensile in this direction, this like. Okay, let me write my. Due to moment my, the moment at point A creates compressive stress. Due to mz, the moment at point A creates tensile stress. That's why we will take. Let me take a compressive as negative. Due to that it compresses, so that decreasing the length, that is decreasing value. So we will take compressive as negative, and tensile as positive. That is positive. Similarly, we are going to find for the point B, for point B, stress in point B. Okay, this is, oh sorry, then stress in point A will be equal to minus myz by, this is a z a, okay, z a by iyy plus mz into ya by izz. Okay, now stress in point B. Now let us take the consideration. Due to the at point B, due to this load, we are getting the layer compressive downwards. Okay, due to this it is compressive again. Due to the my also it is going to compress. Now let me take a my compressive, negative direction. Okay, mz compressive. That is sigma b equal to minus my into zb by iyy minus mz into yb by izz. We know that iyy is moment of inertia along y axis, and izz moment of inertia along zz axis. This is for point B. Similarly, stress in point C, that is, let me take for point C, this is tensile, and this also tensile for point C. Okay, My tensile, that is positive, Mz tensile, that is also positive. Now we will get sigma c will be equal to My Zc by Iyy plus Mz Yc by Izz. These are the values. Let me take for point D. This is tensile, okay. This is compressive, okay. Due to My, that is tensile, point D, positive, that is Mz, that is compressive. That is negative. Then sigma value, sigma D is equal to My into Zd by Iyy minus Mz into Yd by Izz. By obtaining the values, we can find the maximum stress values. That is at point B we get maximum compression, and at point C we get maximum tensile. Okay. Now let me represent using the diagram. Let me take if it is a section, the dotted lines representing towards the axis is compression, that is compressive. If the dotted lines, if the arrows representing away from the axis represent tensile, okay. Now for y axis, we will draw the stress diagram, okay. This is the y axis. This is the y axis. The moment is in this direction, so that this side we will get compression, compressive force, compressive stress, okay. And this side we get tensile. As I said before, tensile represent away from the axis and compression towards the axis. Okay. Similarly, we will draw for z axis. Now let me represent the points here. Okay. A, B, C and D. This is the moment mz. For z axis, this is the z axis. The moment is my. This is compression. And this is tensile. Okay. This is the points A, B, C and D. As shown in the both figures, we can see at the point, due to the y-axis moment, there is tensile stress. But due to the moment along z-axis, we get a compressive. Both are opposite, so we will not get a maximum compressive or tensile at point A. Okay, we will not get maximum values at point A. If we take point B, due to the moment along y-axis, we get compressive here. Similarly, due to the moment along z-axis, we get compressive here. So that maximum compressive stress will be here at this point. At point C, we get tensile, and due to this moment also tensile. So we get maximum tensile stress. These are the based on the diagrams, we can find that maximum compressive stress and maximum tensile stress. Okay, now we are going to discuss about neutral axis. Neutral axis. Since we are getting the maximum values at these ends, the neutral axis will be near to the AD axis. That is, this is the, let me take, this is the axis. A, B, C and D. This is the load. This is the theta. For finding the neutral axis, the angle made by the neutral axis is taken as, let us take alpha. Then for finding the neutral axis, tan alpha will be equal to, since we are taking angle with respect to the z axis, so we get izz by iyy tan theta. Using this relation, we know the values of IZZ and IYY and theta angle, so that we can find the alpha value, that is equal to tan inverse of IZZ by IYY tan theta. By using this, we will get the neutral axis. So okay guys, this is the full topic about the unsymmetrical bending. If there are any doubts, please comment below. Thank you guys.